Hello everyone, good afternoon. And I want to first thank the organizers for putting together this wonderful workshop and for inviting me here. This is my first time at Lumini, but I have heard so many good words about here. Okay, so today really it's my great pleasure and honor to talk here about our recent work on diffusion models. We'll just start. As everybody knows that AI has gone a long way. Recent years, we have seen the meteoric growth of AI models. Among many features, I think one key feature for the current AI model is that it goes from more discriminative AI to more generative AI. Where by discriminative AI, I mean that the main goal is to do classification and make prediction upon seeing a new data sample. And whereas for generative AI, the goal is to generate new data or new instance. Okay, so diffusion models in this generative modeling era hold tremendous promises. And they are first proposed to for image synthesis, but they have received a lot of successes far beyond computer vision. Okay, so as many of you probably know, that diffusion models are now recently used to generate protein structure, and this is from David Baker's lab, where they propose a diffusion model framework to generate for protein design, and he has won a Nobel Prize, not for this, but previous for computational biology of protein structure. Okay, and in reinforcement learning, diffusion models are used to model complex policies and generate plausible policies. And in science applications, diffusion models are used for climate modeling, medical imaging, and also in material sciences. So as you can see that it actually has been quite successful in and have great impact in various domains. Okay, so over the 2 or 3 years, there has been tremendous interest and new findings from the theoretical community trying to understand why diffusion models work so well in practice. And here, this is a very incomplete list of prior work that devoting to the study of diffusion models. And this work includes some of us sitting here in the audience, including Xingho, for example. And diffusion models, the main goal is to generate new data sample Y from the target distribution, where you are given a bunch of training samples from the target distribution. And this is distribution in the D-dimensional space. Okay, so a natural approach when you see this is to directly estimate the density of interest and generate new data sample from the learned density. So a natural way to do this is to directly model the density in some parameterized class. For example, you can write the density as follows: e to the minus some function f over theta, and f of theta, and divided by the normalizing constant. Okay, so after you write this in this way, so the goal is to find the theta, and so that you have your learned density, then you can generate from that learned density. Okay, so after writing this, you can use a maximal likelihood, or if you're Bayesian, you can use a maximal of posterior to find this theta. However, often the case, this is intractable in practice. The reason is because you have this annoying normalizing constant z of theta. So either you will run an extra CMC to estimate this z of theta, or you should restrict your parameterization class to be a really small class, so you can either compute directly of this z of theta or estimate the z of theta. Okay, so another approach is to go through the score estimation, where the sign score function is defined as the gradient of log marginal density So once you take the gradient of log density, you can see that this annoying normalization constant z of theta just disappears, and it equals to the minus of gradient of your function f of theta. Okay, so here on your right, I have plotted the score function, the vector field, and the contour of the target distribution, which I chose a mixture of two Gaussian distribution. And you can see that the score function does contain a lot of information. It points to the higher, points to the regime of higher density. Okay, so actually, this is it's a useful approach where you don't need to care about the normalization constant anymore. So just to set up the framework and make sure that everybody is on the same page, diffusion model contains two stochastic processes, one forward process. This is easier. Suppose that your random variable x0 comes from your target distribution P of data. You just gradually add noise to diffuse your distribution so that it eventually becomes a pure noise. Usually people choose the pure noise to be Gaussian so that you can add Gaussian noise to diffuse your signal. This is simple, and okay, so just remember the notation. I will use alpha t as the coefficient in front of the xt minus 1. And this can also be written as xt in terms of the original distribution x0. Okay, so I write alpha t bar to denote the product of the previous alpha t. Okay, and what's tricky is the reverse process. So the reverse process goes from the pure Gaussian noise, and you want to gradually convert from a pure noise to your signal, which in this case is an image of a horse. So it turns out that there are many feasible strategies to do that, as long as you have feasible estimate of your score function. In fact, a standard result in SDE literature tells you that as long as you know the score function, the gradient of log density, you can write down the reverse SDE so that you can generate sample from this reverse SDE. There's reverse SDE in this case is a simple OU process. Okay, where that's the reverse SDE, the drift term only depends on your YT and the score function. And also you can write down the reverse ODE, where both of these processes share the same marginal distribution. Okay, so with that, now a common approach is to do this in a divide and conquer way, in the sense that people will divide this into two phases. The first phase will be trying to do score learning or score estimation or score matching, where you use your training samples to learn the score function. Okay, this is a purely statistical task. You can use your favorite statistical method to do score estimation, or you can also use your neural network to do that, up to you. And the second step is to do data generation, in the sense that once you are given the score estimate, and with those score estimate, you want to generate samples. You want to recover the target distribution. All right, so in this talk, we'll mainly focus on the second part, but I will just quickly mention the first part, the score matching. Why is this called score matching? Basically, if you think about this forward process, you start from a target distribution, and each time you add noise to your target distribution. And by Tweedy's formula, the score function can be written in this denoising form, where you want to find the conditional expectation of your noise given the linear combination of a signal plus the noise. Okay, once you have written in this way, this is a purely a denoising denoising problem to recover the score. Okay, so that you can think about many different methods to do that. For example, you can use non-parametric method, the kernel method to find the score, or you can use approximate message passing algorithm, or you can use neural networks. And some people, there's some very nice work proving that if you do things like this, you can actually have a minimax optimal estimator for the score. Okay. And now in terms of data generation, now the two popular mainstream approaches are these two approaches, one stochastic one and one deterministic approach. Let me quickly go through that. It's just super easy to describe. This is our forward process, and think about our denoising process where the stochastic sampler, which is also called a DDPM, short for denoising diffusion probabilities models. It does something like follows. So this is an iterative procedure. You start with a pure Gaussian noise, okay? And at each step, you take a deterministic function of the last step, yt, and plus your score estimate. Because here, we assume that the scores are given, okay? So now this is a purely deterministic function of your last iterate, and you plus you add some independent Gaussian noise and take the linear combination of those. Is that clear? So that's the DDPM procedure. Not too hard. The deterministic sampler is even simpler. So the deterministic sampler just take a linear combination of your last step, yt, and your score function. Okay, purely deterministic if you're given the score estimate. All right, so we will try to analyze these two procedures. All right, so let me first tell you our previous result on the convergence theory for the DDIM, the deterministic procedure. And it turns out somehow in literature, the deterministic procedure is harder to analyze than the stochastic version. I guess maybe the intuition is that for the stochastic version, if you add some noise, you sort of smooth things out, then the procedure is actually easier to analyze. But think about deterministic one. Once you are given the Y capital T, okay, you generate yt from the Gaussian noise, the entire procedure is sort of fixed if you have access to the score estimate. Yes?
Remind how you fix alpha t?
Okay, so the ST, so we divide this text into two. And step one is to do score estimation, where you use your training samples to estimate the scores. So S of t is just the estimator of the gradient log marginal. Oh, the alpha t. Okay, so I will tell you how to choose alpha t here. The alpha t is selected, is pre-designed, so pre-chosen. And this is a,
Is it any alpha or?
No, for a fixed choice of alpha t, a fixed sequence of alpha t. Yes, I will specify that, yes. Yeah. Any other question? All right, let's proceed. So our theorem states as follows. Under some mild assumptions of target distribution, I will tell you a bit later what's those mild assumptions. And the DDIM sampler satisfies the following. So the TV distance between P of x1, remember x0 is our target distribution. X1 is the target distribution at slightly amount of noise. So actually the Px0 and Px1 are very close to each other. And your Y1 is the one generated from the DDIM. It's an iterative procedure. You run this until Y1. All right, it's bounded by three terms. Yes?
Px1 and Px0 are
very close to each other.
If x0 is
yeah, that's, yeah, that's, yes. If, yeah, but yeah. Yeah, good point. Yes, yes, not in TV. Yes, but okay, yeah. Okay, so now if you ignore the second and the third terms, okay, and only look at the first term tells you that if you're interested to find a distribution that is epsilon close to your target distribution, then the number of steps it takes is of order d over epsilon, where you take d over t to be smaller than epsilon. You solve for t, then the number of steps, the iteration complexity, is of order d over epsilon. Okay, so now let me tell you what is the second and the third terms. Well, so in order to do that, I will tell you first about the mild assumptions that we put on the target distribution. So the first assumption we put is that your target distribution is supported on the it's supported the L2 norm of x0 with high probability is bounded by a very, very large constant that can grow with t. Okay, so we only need this x0 to have a compact support. Okay? And in fact, this is very general. We don't need any assumptions like log concavity, which is often assumed in the literature of diffusion models. And we don't require any smoothness assumption on score function or the distribution. Okay, and that's the only assumption that we make on the target distribution. The next set of assumption is about the score estimate, because we divide this into two phases. So we have the score estimate, where we assume that they satisfy that on average, in the L2 sense, on average, your score estimate ST is very close to your true score S star. All right, this is typical assumptions and it's assumed in the literature. Okay, but the actual assumption that we make is about the Jacobian estimation error. We assume that the Jacobian of ST is somehow on average close to the Jacobian of the true score. Okay, so this is not super nice, but this assumption sort of constrained that your score estimate cannot be too crazy. It needs to kind of be smoothed somehow. It is smooth somehow. Okay, cannot wiggle too much. All right, so those are two set of assumptions, one on the target distribution and these two on the score estimate. Okay, so our second and third term depends respectively on the score estimate L2 error and the Jacobian error. Okay, and I want to just say, mention one thing. In order to get a sharp dependence on D, we need to work really hard and use techniques from stochastic localization. And previously, people are only able to get a polynomial dependence on D. Okay, or either get a polynomial dependence on D, or change your sampler a little bit from the DDIM and add a few maybe stochastic correction steps to DDIM in order to have a control of the some metric between your sampler and the true distribution. Okay, and that's the theory for the deterministic sampler. And for the stochastic sampler, the DDPM, similar scaling has been established, D over T, in this paper by Li and Yan for TV, and Benton and al. For KL. Okay, yes?
So the epsilon Jacobi, this is about a d-dimensional object, so would it not depend typically on the dimension?
That's a great question. So here the Jacobian, by the way, this is an operator norm. Yeah, so we wouldn't say that these two terms, they can depend on the dimension. And the coefficient in the front, we don't know whether they are tight or not.
Wait, so which one is tight?
The tight, we mean the first term. That depends on the iteration complexity. Yeah, great. Any questions? All right. So you may say that, okay, so this is a general result for sampling a d-dimensional distribution, but in practice, maybe practical distributions, they have low intrinsic dimensions, right? That's what people observe in image data and text data. So I'm going to quickly mention this before going to details about our acceleration step. So maybe some of you have heard me talking about the adaptivity of DDPM. Basically, in our two separate work, we discussed the adaptivity phenomenon for DDPM, where we show that DDPM, the stochastic sampler, only yields k over epsilon number of iterations for distribution that's supported on k-dimensional manifolds or k-dimensional linear space and things like that. So in the sense that if you have a target distribution that is supported on a distribution with log covering number on scale with k instead of d, because in general, a d-dimensional distribution would have log covering number scale with d. If you have that scaling with k, then we can prove that the number of iteration instead of d over epsilon can be improved to k over epsilon without changing the sampler itself. In the sense of the DDPM algorithm, as it's in its original form, will automatically adapt if your target distribution is actually k-dimensional. Yes?
I'm just wondering, so Kullback Leibniz means in particular the measures are equivalent or absolutely continuous with respect to each other, but one distribution lies on the submanifold. So you really get the support, right? I know that there's total variation in these kind of results.
Yeah, so here actually these results can be improved for TV as well.
Yeah, but TV is worse than Kullback Leibniz. So I'm wondering, so identifying the submanifold is kind of a difficult problem. If you have a distribution on the submanifold,
right. Yeah, so I guess that your question is mainly on the second and the third, the arrows, that we talk about score estimation. So if we assume here the score estimation is accurate enough, but you are right. If you want to, yes, right. Yes, right, yeah. Okay, for the other adaptivity result we have is that the DDPM sampler in its original form satisfied that the iteration complexity if your target distribution is actually generated from a mixture of spherical Gaussian, and then the number of iterations instead of d over epsilon, it's actually 1 over epsilon up to log factor. In the sense that you don't have to pay a price in terms of the dimension d. Although mixture of Gaussians, they are very full dimensional objects, but diffusion models just can sample them really fast in 1 over epsilon number of steps. Okay, so I'm happy to talk about these two results offline, but since some of you have heard me talking about this, I will instead focus on the acceleration steps for diffusion models. So so those two results are for some specific distribution where they have some low intrinsic dimension. But in general, this d over epsilon number of steps is still very, very high for general distribution. So in fact, the diffusion models, they are actually suffered from low sampling speed due to extensive function evaluation in the sampling process, where in each step, you need to evaluate the score function. Usually the score function is some large neural network, and evaluating those large neural networks takes a long time. For example, you can see this is a comparison between DDPM and GAN. to sample 50K images, DDPM takes like 20 hours, whereas GAN only takes less than 1 minute. So the one active area of research is to sort of speed up the diffusion models. And there are various ways that people develop to speed up diffusion models. One way is training-based, where it's based on distillation. What it means is that you sort of distill a pre-trained diffusion model. So you have a very large model, and you distill a small model out from this large model, and then use this small model to generate your samples. Okay, so of course it's gonna run faster, but it requires additional training. And the other set of paradigm people propose is training-free speedup, where you directly evoke the pre-trained diffusion models and generate samples without additional training. So in this part of the talk, I want to I will try to design a training-free sampler that is provably faster than DDPM or DDIM. Is that clear? Okay, so how are we gonna do it? Well, so let me first tell you our proposed method, and then I will give you some intuition on why this should work and why we can design acceleration scheme based on that. Okay, so this proposed method is actually very easy. What does it do? You first compute a midpoint, we call it YT minus, or YT bar, YT minus. And then we update our YT minus 1 based on both YT, your last iterate, and this midpoint. How are we gonna do that? Well, so you see that when we update our YT minus 1, it still looks like original DDIM scheme. Okay, the formula is exactly the same with DDIM, just plus some momentum-like term that depends on your score function. Okay, and that's how we update our YT minus 1, but for the midpoint, it's actually also just a deterministic function of YT based on your, if you're given the score estimate. Okay, very simple. The only thing that requires is the additional step of momentum-like term. Okay, but you can see that it requires additional score estimate, additional evaluation of the score function, where you need to evaluate your score function at YT minus 1. Any question about this procedure?
Is it somehow related to higher the schemes for these?
Very good question. I will talk about that later. It's actually just one form of a higher order acceleration scheme. Yeah. Okay, so here are some simulations, and you can see compared to the DDIM, the original DDIM procedure, ours, if you fix a number of function evaluation, we do generate much crisper and clearer images for this church data set. You can also see the performance on other data set. All right, so let me give you some intuition on how we propose that algorithm and some generalization to the higher order scheme. Okay, so how do we come up with this algorithm? Well, so if you think about the DDIM procedure or the probability flow ODE, you can actually write the YT minus 1 as a linear, the summation of your YT with some particular choice of alpha t, I will tell you later, plus this integration of the score function. This can be easily validated. Remember, score function is just a gradient of log density. Okay, so what is S star gamma, well, this S star gamma is basically just the score function correspond to this continuous. Okay, so gamma is a continuous number between 0 and 1. It's just some summation of a linear combination of x0 and the Gaussian noise. Okay, so then if you want to design a sampler, then we need to discretize this equation, right? Otherwise, you need to evaluate this integration, and that requires you to learn the score function everywhere. So if you want to approximate this, probably the simplest way is to approximate this integration by the endpoint. If you do that, you can directly take the function to be the one that at endpoint, because the interval is very short, and then that recovers the original DDIM. Okay. However, that gives you d over epsilon number of iterations. And if you want to find a refined approximation, of course, you can use first order Taylor expansion and take the endpoint plus the derivative time. And you don't have access to the derivative. So what you do is you use the two endpoints to approximate the derivative. So that's the whole point for this design. And that actually gives you the proposed method I was talking about earlier. So if you use second order approximation, you get exactly this. And another way to write this is exactly what I described earlier. Okay, but you don't need to stop at the second order approximation. You can think about higher order approximation, where here we use Lagrange basis polynomial to approximate this function. Okay, with to the kth order. If you do that, you can. Do I need to? Okay, so basically you want to approximate this complicated function, and you can try to approximate that, use Lagrange polynomials, and have k different points, and sort of estimate their corresponding score function at k different points, and then construct an estimator for the integration, and that's exactly the estimator for the function, the score function. And if you do that, we can actually prove that the number of iterations now is of order d to the 1 plus 2 over k over epsilon to the 1 over k. So if you take k equal to 1, so basically that gives you, that is exactly if you do nothing, this is just the original DDIM. If you take k equal to 2, that gives you accelerated version for DDIM, a second order acceleration. And if you take k to be really large, but fix a fixed constant, so it cannot grow with d or n or any parameters, then you get an acceleration. Okay, but of course, if you run that increases the number of score function evaluation. We need to trade off between these two. Okay. All right. If you prefer a convergence result instead of iteration complexity, this convergence result basically can be described as the TV distance is bounded by d to the 2 plus k divided by t to the kth power. So you can see in terms of t, you previously have 1 over t. Now you have 1 over t to the k. So you can choose k to be really large, then you get an essential amount of acceleration. Okay, I think I'm running out of time. So just to conclude. No? Okay. Okay, yes, question.
What is the dependence on the square error? In particular, do you need higher order derivatives?
Yeah, that's a very, very good question. So the score estimation error, of course, you need a more stringent assumption than the L2 average L2. Here we need this, the L2 error of the score at not only those T points, but also the midpoints. So remember that in the midpoints, we break the interval into K, we find K midpoints. And we need the score estimation error at these K midpoints to be also close. Does that make sense? Yeah. Okay. Yeah, that's a great point. That we don't want to assume a higher order accuracy for the score estimation error. But here we also have the Jacobian Jacobian error that cannot be ignored. All right. Maybe, or just if there's any other, yes.
So maybe this requires K to be super constant, but I guess if you just cared about workload calls, and you wanted to figure out what's the best K so that like the minimum number of workload calls, is it clear what K you should get?
Okay, so here you can see the number of score estimation of this scales is of order that, of that order. I don't know, if you care about the speed up, you should choose K as large as possible. So you get a speed up in terms of dependence on epsilon. But that of course requires, sorry?
But we need more calls per one step.
Right,
so I guess
right.
If you just care about the total number of calls you make, like what is the best K?
Well, still it's okay, so you see the number of score function evaluation. You can just pick your budget and find K as large as possible. Yeah. Okay, any other questions? Yes?
So for this last result that you have shown,
Use the mic.
yeah, so in this result, you have the upper bound on the TV distance. In the previous results, you have the KL.
Yes.
Here also you pass through KL for bounding TV. So you use Pinsker somewhere or no, to directly bound TV?
Yeah, so for both results, when we state the result in TV, we directly deal with TV. Yeah. That's a great point. Yeah.
So thank you very much.
We haven't concluded. Oh, well, I will conclude really fast. So what I did,
Take all the time you need.
what I did is I described sharp convergence theory for the deterministic sampler. And also I mentioned diffusion models are automatically adaptive to distribution with low covering number or GMMs. That's very nice for DDPM. Also, I described several acceleration scheme for DDPM via higher order approximation. Okay, so you can find our papers in these two here. That's the main papers that are relevant to this talk. Thank you very much for your attention.
Thank you.
Oh, I don't think I have answered your question about the alpha T, the step size choice. So the step size choice, for all these results, they are only established for one particular choice of sequence of step size choices. And that's step size choices are commonly used in the literature, where what we did in the forward, if you look at forward process, so basically you take it exponentially increasing up to some point and then stay constant. That's the step size we use. Yeah.
Any more question or comment? Okay. So if not, thank you again very much. Nice talk.